Behind this whole AI revolution, everything from the chatbots we use to self-driving cars, there's this massive hidden challenge. We're literally building these incredible silicon brains, but the real trick? It's figuring out how to wire them all together without the whole system just grinding to a halt. So let's dive into how we're solving what might be the biggest traffic jam in history.
The AI data centers that are going up right now, they're not just big, they are absolutely monumental. We're talking about connecting over 1 million individual processors, or XPUs, into one single massive system. Imagine a city of 1 million silicon mines, and they all need to talk to each other instantly. And right there, that's the core problem, isn't it? When you have 1 million different things all trying to talk at once, you don't really get a conversation. You just get noise. You get total gridlock. So how on earth do you solve what is literally the world's biggest data traffic jam?
Okay, so before we get to the really cool solution, you first have to appreciate just how big the problem is. For decades, we've been building our data superhighways with the same basic material. And, well, we've finally hit the end of the road.
Yep, good old copper wire. It's been the workhorse of electronics forever. For years and years, we've just sent data as little electrical pulses down these tiny metal pads. But now, as we're demanding way more speed and way more connections, the basic physics of electricity and copper are starting to fight back. It's creating a bottleneck that you just can't fix by making the old roads wider.
This gridlock actually has a name. It's called the I/O bottleneck, and you should think of it as the ultimate speed limit on AI. I mean, it doesn't matter how fast your processors can think if they're just sitting around waiting for data to show up. This bottleneck, it's the central villain of our story today.
So what's actually so bad about copper? Well, trying to push more and more electricity through it is exactly like trying to force more cars down a street that's already too narrow. You just end up burning a ton of power, which then creates a massive amount of heat. On top of that, the signal itself starts to fade over any kind of distance, and it's super easily disrupted by interference. We don't just need a wider road, we need a whole new kind of road.
And this is where the solution comes in. Instead of pushing electrons through copper, what if we could send photons, actual particles of light, through optical fiber? The advantages are just staggering. Way less power, so less heat. Much lower latency, so it's faster, and the signals can travel huge distances without any loss. The fundamental shift we need is to go from electricity to light.
And let me be clear, this isn't just a simple upgrade. It's a fundamental change in how we move data around. It's all about trading in those traffic jams of electrons for the light-speed highways of photons.
The big breakthrough that makes all this possible is called silicon photonics. Essentially, it's the science of building microscopic optical parts. We're talking tiny lasers, modulators, detectors, and putting them directly onto the same silicon that we use to make computer chips. This lets us build those highways of light right there, on the chip itself.
But how do you actually get the data from the processor onto this new highway of light? Well, the answer is all about moving the on-ramp closer and closer and closer to where the traffic is actually coming from. For a long time, the standard way to do this was with something called pluggable optics. So imagine your computer chip is a big factory. In this old model, the data, our electrical signal, has to take this long commute across the city, which is the circuit board, to get to a whole separate device. That's the on-ramp to the fiber optic highway. And that commute, it's slow and it wastes a ton of energy. The revolution here is to just stop making the data commute at all. Instead, let's build the on-ramp to the light-speed highway right next to the factory, all inside the same little neighborhood, what we call the chip package.
And this is co-packaged optics, or CPO. We are literally placing the optical engine, that's the thing that turns electricity into light, right beside the main processor. By making that electrical path super short, we solve so many of those old problems of power, heat, and signal loss.
You can really see a clear evolution here. We started with onboard optics, which was still a bit of a commute for the data. Now, the mainstream approach is CPO, which puts the optics right there on the chip's foundation. And the future? That's optical I/O, or OIO, where the optics will be practically fused with the processor itself. Each step just brings the light closer, making the whole connection faster and way more efficient.
And the results are just incredible. Compared to that old pluggable method, co-packaged optics uses less than half the power and has less than 1/10 of the latency. I mean, that is a game-changing leap in efficiency. It completely changes the performance math for these huge AI data centers.
Now, a technological jump this big doesn't just change a few designs. It kicks off a fierce competition. The race to build the fastest, most efficient connections for AI has officially started, and it's being fought with beams of light.
And one of the clear leaders in this race so far is Broadcom. Just look at this timeline. Every 2 years, like clockwork, they've dropped a new generation of their Tomahawk switch chip, and each time they're integrating more advanced CPO. This kind of consistent execution has given them a really significant head start.
And this chart really puts that lead into sharp focus. Now, we all know NVIDIA is an absolute titan in AI processors, but in this specific race, the race for 102.4 terabit per second optical switching, Broadcom is about a full year ahead. In the world of high tech, that is an eternity.
But this isn't just about one company versus another. There's a much bigger battle of philosophies going on here. You have the Ultra Ethernet Consortium, or UEC, which brings together this huge group of industry players. Their goal is to create an open, standardized way for AI systems to connect, which directly competes with closed, proprietary systems. It's that classic battle, open collaboration versus a single lockdown solution.
So, we did it. We've solved the great traffic jam by replacing those congested copper streets with what are basically limitless highways of light. This huge leap, all powered by silicon photonics and co-packaged optics, is going to enable the next wave of AI. But it does lead to one final, really interesting question. Now that we're moving data at the speed of light, what's the next barrier we're going to hit? What physical limit comes after speed itself?